Hi, my name is Emery Pearson, and I'm going to present our joint work with Emmanuel Hartmann, Martin Bauer, Nicolas Charon, and Mohamed Daoudi, called A Framework for the Analysis of Unregistered Human Body Shapes. In our work, we provide a framework for human body deformation that is able to solve related tasks, such as shape interpolation or motion extrapolation. We work on scans, meaning that there's no non-parametrization, with high details, but topological noise, lack on hands and fees. The key ingredients of our approach will be to work on a subspace of learned deformation with a tunable reparametrization invariant Riemannian metric. Finally, we'll use varifold to bypass the need of registration. In related work, we find elastic shape matching that does a similar idea, but the problem is that they work with spherical maps, and the spherical parametrization of a shape is a hard problem and is sensitive to topology. At the same time, deep learning for 3D has come across with autoencoders, but encoders often lack expressivity. The map from latent space to nonlinear shape space also lacks generalization. And some networks tend to overlearn the parametrization when it's trained on parametric data. The first ingredient is a Riemannian latent space of human bodies, which is disentangled in pose and shape, and constructed using motion training data. It is equipped with the pullback metric of the parametrized human shape space, meaning that a path in the latent space corresponds to a geodesic in the shape space. The advantage of the disentangled shape space is that we can disentangle paths of shapes easily by providing the path of pose and the path of shapes. The second ingredient is to equip our space with the Sobolev metric of order 2. It contains 6 different terms, which are the kinetic energy of the path, 3 physical terms of order 1 penalizing shearing, scaling, and bending, the completion of the order 1 metric, and an order 2 regularization using the Laplacian. The third ingredient is to bypass the registration using the varifold metric, which provides a distance which is invariant to the parametrization of surface and robust to noise. It was used previously for numerous numerical surfaces problem, and also in the context of human body for sequence comparison. The final idea, to interpolate between 2 scans, is to first start with a constant path of the template. We iteratively move the geodesic until the endpoints of the path correspond to the 2 shapes parametrized, which are at 0 varifold distance of both scans. Experiments to validate our method are used by training on dynamic forest meshes, with 10 mini-sequences left for testing and 90 scans used for registration. We applied our approach on mesh registration, shape interpolation, and motion extrapolation. We compare our method against deep latent spaces, which are limp, Arab-Rec, and 3D coded. For mesh registration, we observe that we produce consistent registration across different poses, as the opposite from limp, which tend to have poses that are far to the ground truth. Arab-Rec and 3D coded produce nice registration, but some of the failures tend to be worse than our failures. For shape interpolation, we can see the consequences of this, with limp produces a bad path because of the bad endpoints, and Arab-Rec producing a non-plausible deformation by shrinking the hands, while ours produce a plausible motion between the 2 shapes. We observe similar behavior for motion extrapolation. The path of limp is bad because of the bad endpoints, and Arab-Rec tends to modify the shape of the hands, while ours produce a consistent lifting of the knee. We apply our method with motion transfer easily by swapping shape codes between the woman moving and the 2 men. We can also do human shape generation by providing a generative model on the tangent space of the template. To conclude, we provide a Riemannian deformation of human shapes, which was applied to unregistered shapes and allows for interpolation and extrapolation. It can be applied to other problems like generation and motion transfer of shapes. It is limitation that we will work on the future, like time computation and dependence on data. Thank you for listening.